Thank you to everyone who watched my first video and left a nice comment. I appreciated every word. N-dimensional Euclidean space is a space where you can have at most n mutually perpendicular lines, and the sum of the internal angles of any triangle is 180 degrees. If you don't know what non-Euclidean space is, don't worry about it. I'll mention it a lot in this video, but it can be safely ignored. So when n equals 2, you get 2D space, with up, down, forward, back. When n equals 3, you get something like our universe, with the additional directions left and right. When n equals 4, nothing special happens. There's now a new axis perpendicular to the first three, giving us the directions ana and kata. These function identically to left and right, just rotated 90 degrees. A lot of people, being unable to easily comprehend four spatial dimensions, assume it's impossible and just mumble something about time. But I assure you, the fourth dimension is not time, it's just a fictional space that is equally mathematically valid as 3D. This is what the fourth dimension looks like. I am a three-dimensional flatlander, so I fell flat on my face. Well, not in my face, it's more like I'm on my brain. Anyways, while this space is very easy to mathematically define and should be understandable by everyone in that sense, it is very intuitively complex. So, I hope to explain it to you. We can start by explaining my renderer. The way I render 4D in my videos is that I crush the whole 4D scene down to 3D based on the camera orientation, and then I sometimes fade out the back half of the shape, and then I color and fade based on the fourth dimension W component. If something is on your volume, its color is not changed. If it's W plus of your volume, it's orange. If it's W minus of your volume, it's blue. And if it's any further in either direction, it fades out until it's gone completely. In 4D, planes can be fully perpendicular. You might have heard people call planes in 3D perpendicular, but I disagree. These are not perpendicular, they share an axis, they're semi-perpendicular, semi-parallel. These two planes, on the other hand, are fully perpendicular. Also, the dimension of a surface is the dimension of the space minus 1, so surfaces of 4D objects are three-dimensional, the same way that the surface of a 3D object is two-dimensional and the surface of a 2D object is one-dimensional. This isn't the topological definition of surface. When I say surface here, I just mean the surface of an object. In order to get comfortable with 4D, I recommend learning to accept all the weirdness. If you try to fight the weirdness, you don't really get anywhere. In other words, learn things logically first, and then visual intuition comes later with practice. Another thing to learn is that rotation is not axial. If you imagine a 2D scene, what axes do things rotate around? The z-axis? That axis isn't even in their space. No, it makes more sense to say that they rotate in the xy plane. The reason we usually think of rotations happening in axes is that every plane is perpendicular to an axis in 3D, and an axis is easier to describe than a plane. But in 4D and higher, it makes more sense to talk about the plane you're rotating in, rather than what you're rotating around. Because in 5D, now you rotate around volumes, which is 3 axes to describe, rather than the plane, which is just 2. In 4D, you rotate in planes, just like 2 and 3D, but you also rotate around planes. Remember diadicity? As you might expect, diadicity now states that 4 polytopes, called polychora, must have 2 cells meeting at every face. And cells are just the rank 3 elements of a polytope, like this pentagonal prism of the dodecahedral prism. It seems weird that they meet at a face, but remember, 2 planes can be perpendicular, so when these 2 faces touch, there's a plane perpendicular to them, and a rotation happens in that plane to make the cells bend up into 4D to start a polychoron. This is similar to how 2 faces meet in a polyhedron at an edge, and then there's a plane perpendicular to that that allows them to rotate up into 3D to start a polyhedron. Also, faces are not facets or sides. I can't stress this enough. The faces are just the rank 2 elements of a polytope, the same way the edges are just the rank 1 elements. With that, I think we're ready for the strictly convex regular polychora, more simply called the 4D platonic solids. First up is the 4 simplex. With videos like this, it's easy to turn your brain off and just let the nice visuals scroll by, but I want to invoke some audience participation here. What sides do you think the 4 simplex has? If you guessed 5 3 simplices, or tetrahedra, Great job! You have basic pattern recognition skills. This shape is called the 5-cell, or pentachoron, and it has A4 symmetry. Its Schläfli symbol is 333. 333 is a palindrome, so you can tell it's self-dual. Every simplex is self-dual, and its Schläfli symbol is a string of threes. Wait. I forgot to explain what Schläfli symbols are. Let's go over that quickly. Remember that chart we had last episode of all the platonic solids? Well, now it's a 3D chart. You might think we expand it by doing number of faces on the polyhedral cells as one axis and number of cells at a vertex on the other, but that's vague and doesn't allow duals to be flipping, so what we actually do is use Schläfli symbols. I really should have explained what a Schläfli symbol is last episode, but hindsight is 3636. Massively oversimplifying here, but a Schläfli symbol is a list of numbers between curly braces. The Schläfli symbol's goal is to represent a regular polytope. It's easiest to explain in steps. Starting from a Schläfli symbol of length 1, the 1 number tells you how many sides the regular polygon has. These Schläfli symbols with just one number have symmetry I2 parentheses n. Then, moving up to length 2, the second number tells you how many faces meet at a vertex. So 3, 4 is the octahedron, and 6, 3 is the hexagonal tiling. Finally, to extend to every higher dimension, all but the last number is the Schläfli symbol of the facets, and all but the first number is the Schläfli symbol of the vertex figure. These are always read left to right, despite them being kind of backwards from each other. A Schläfli symbol of length n describes a polytope of rank n plus 1. Self-dual shapes have palindromic Schläfli symbols. I hope that side tangent wasn't too jarring, but now we should be able to get back to the platonic solids now that you understand how Schläfli symbols work. Next up is the 4 cube. This one is very popular, and it's the only 4D shape that actually gets talked about, along with the 4 ball. What sides do you think it has? The correct answer is 8 cubes. Again, pretty easy if you've been paying attention. This has B4 symmetry and goes by a few names. Usually tesseract, but it's also called the 8-cell or octachoron more formally. Its Schläfli symbol is 433. The 3-3 at the end means that the cubes at a vertex connect together in a tetrahedral way, so that's why there's 4 cubes at every vertex. This is the vertex figure I was talking about from earlier. In general, the vertex figure has rank n-1, so we say that the vertex figure of the tesseract is the tetrahedron. Lastly, we have the 4 orthoplex. This one is a bit trickier. If you guessed 16 tetrahedral sides, you are correct. That's why this shape is called the 16-cell, or hexadecachoron. This, of course, also has B4 symmetry. Its Schläfli symbol is 334, which is just the tesseract symbol read backwards, since the n-cube and n-orthoplex are always duals. The vertex figure is the octahedron, and this shape tiles space, 3 to a face. I could look at this all day, but let's get back to the video now. That went by really quickly, mostly because I already explained most of these concepts in episode 1. Okay, this didn't work last time, but let's try the joined 4 cube, just for completeness. Just put that one up there. Alright, now I'm gonna push this one up. Yes, okay. Now just tip the whole thing over. Come on, come on. Yeah, okay. And the last one will just slide into place. Nice. Oh my god. Wait a second. This thing is regular. It worked. This is the 24-cell, or icosatetrachoron. It's the most interesting platonic solid in 4D, and a favorite amongst fans. It tiles space, is self-dual, and has a Schläfli symbol of 343, and the joined n-cube is only regular when n equals 0, 1, 2, or 4. It has its own symmetry group, F4, and there are no other F-class symmetry groups in any higher or lower dimension. We'll get back to the 24-cell. I want to explain why it's so cool, since I haven't seen anyone else explain its mathematical triple cubic perfection. But for now, let's continue with the rest of the 4D platonic solids. Remember how we make polyhedra by folding polygons up at a vertex, and we make polychora by folding polyhedra up at an edge? Well, we can use ditopple angles, also sometimes called dihedral angles, to figure that out. The diatonal angle of a regular polytope is the angle between two neighboring facets. When folding, if we have two of a shape, they make a ditope, but three or more and we get something non-degenerate. The tetrahedron has a diatonal angle of approximately 70.52 degrees. That's smaller than 120 degrees, so we can fold 3 tetrahedra at an edge to get the 5 cell. The 5 cell is the first simplex to have a symmetry group that doubles to a unique symmetry group, fittingly called A4 times 2. By placing two pentachora dual to each other, the facets and vertices map onto each other and the symmetry doubles. The order of a symmetry group is the number of ways a symmetry group can be oriented and look the same. A4x2 has twice the order of A4. The tetrahedron's diatonal angle is also smaller than 90 degrees, and folding 4 around an edge gives us the 16 cell. It has 2 perpendicular rings of 4 vertices. Finally, it's also smaller than 72 degrees, and folding 5 gives us a platonic solid we haven't seen before. The 600 cell, also called the hexacosacoron, has the Schlafly symbol 335. The last number being 5, and 5 tetrahedra folding at an edge is no coincidence. Its vertex figure is 3-5, or the icosahedron, which has opposing vertices, so the 600 cell has rings of vertices. Specifically, it has 12 equivalent rings of 10 vertices. What I mean by a ring of vertices is that a 2D plane that passes through the 600 cell's center can be rotated to fit 10 vertices and 10 edges at a time, and the vertices form a regular polygon. The 600 cell has 9 vertex layers, going vertex, icosahedron, dodecahedron, larger icosahedron, icosododecahedron, and then it's symmetrical to the other side. Its symmetry group is, as you might have guessed, H4. The tetrahedron's diatonal angle is greater than 60 degrees, so folding 6 is hyperbolic. This is a regular polychoron, but it isn't a platonic solid because it's infinite. The next platonic solid is the cube. It has a diatonal angle of 90 degrees, so we can fold it 3 to an edge, but 4 to an edge is Euclidean. Folding it 3 to an edge gives us the tesseract, which has 2 perpendicular rings of 4 cubes, just like its dual having 2 perpendicular rings of 4 vertices. The 4 cube isn't just any old n cube. It's the only n cube to have the distance from the center to its vertices, the circumradius, be equal to its edge length. Folding 4 cubes to an edge gives us the cubic tiling, meaning that the most played video game in the world takes place on a polychoron. Octahedra have a diatonal angle of approximately 109.47 degrees. That folds into the 24 cell, 343, and 344 is hyperbolic. The 24 cell is really interesting for a lot of reasons, but I'd like to draw attention to the fact that it doesn't have asymmetric facets or vertices. Every other platonic solid in every other dimension either has asymmetric facets or asymmetric vertices. The 24 cell has bisymmetric facets and bisymmetric vertices. Dodecahedra have a diatonal angle of approximately 116.56 degrees. That's less than 120 degrees, so it folds into 533, but 534 is hyperbolic. The astute among you already predicted the existence of this shape, since 335 is not a palindrome, so the 600 cell must have a dual that's not itself. This thing is called the 120 cell, or dodecacontachoron. Since the 600 cell has 12 rings of 10 vertices, the 120 cell has 12 rings of 10 dodecahedra. These are very pretty to spot as it rotates. I built a net of this shape and made a video about the process of doing so. Lastly, we have the icosahedron. Its diatonal angle is approximately 138.18 degrees, which is greater than 120 degrees, so it's immediately hyperbolic. That's the 2 remaining platonic solids, the 120 cell and 600 cell. These have a really beautiful symmetry group. I'm a huge fan of H-symmetry. These 6 platonic solids together are very cool. There's 3 boring ones and 3 special ones. And even of the boring ones, 2 of them have unique features. The pentachoron just truly sucks, though. Now that you know the platonic solids, I think it would be good to show you this chart again. On this axis we have 333, 433, and 533, and then going up on this axis we have 333, 334, and 335, and then over here we have the lone 343. Okay, now I can explain the 24 cell and why it's really special and unique. It's going to take a lot to get to that point though, so just bear with me for a moment while I talk about some seemingly unrelated things. What's a demicube? Imagine you have an n cube. We'll have n equals 3 for this example. Select half of its vertices and make sure that no edge has two selected vertices. If that seems too manual for you, number each vertex with a binary number, where every axis is 1 bit, and then select the vertices where the sum of the bits is even or odd. Now we take the convex hull of those vertices, and we get the n demicube. You can think of the convex hull as shrink wrapping an object, but remember that this isn't quite accurate, since it doesn't sag at all. When you take the convex hull of an object, you get a convex shape with the smallest volume that contains all of the object's points. Convex just means it doesn't have any holes, dips, or spikes. The symmetry group of the n demicube is Dn, except not, because the 4 demicube is actually the 4 orthoplex, so the 4 demicube has B4 symmetry instead of D4. So what is Dn then? Well, I was originally going to explain how there's 3 ways to have Bn, but that took too long, so instead I'm just going to say that Dn is the symmetry group of an n-cube with 2 types of vertices, in the same pattern as described earlier. Let me make this extremely clear. D4 is not B4. Even though the 4 demicube has B4 symmetry, D4 still exists. For example, if you truncate half of the vertices of a tesseract, you get a polychoron with D4 symmetry. Why is the 4 demicube the 4 orthoplex? Well, if you have 2 opposite demicubes, and place them 1 unit away in the next dimension, and take the convex hull of that, you get the next demicube. If you take 2 dual simplices and offset them in the next dimension and take the convex hull of that, you get the next orthoplex. Since the 3 demicube is the 3 simplex, the 4 demicube is necessarily the 4 orthoplex. This also means that D3 and A3 are the same. Pretty funky, huh? If this feels like a lame coincidence and not satisfyingly inevitable, I have a webpage in the works about Coxeter-Dinkin diagrams, and to me, the Coxeter-Dinkin diagram explanation is just endlessly satisfying. Alright, so now you understand what a demicube is, and that 4D is the only dimension where the demicube has more symmetry than demicubic. Let's do something random and stupid. Take an odd and even 3 demicube and compound them together to get the stella octangula. These 2 demicubes are taken out of the same set of cube vertices. Because these 2 are placed that way, the symmetry group doubles from D3 to B3. If we place a 3 orthoplex, dual to the 3 cube vertices, the symmetry of the orthoplex aligns with the symmetry of the 2 demicubes, and the compound maintains B3 symmetry. Notice something really important. If we rotate the compound by 90 degrees, the 2 demicubes swap and the orthoplex stays where it is. This is why adding another demicube to the demicube doubles the symmetry. One demicube has 180 degree symmetry in that plane, but placing 2 allows them to swap, giving you 90 degree symmetry. Also, another important thing is to notice that the demicubes still have D3 symmetry within the compound. This means that rotating the entire compound, focusing on one demicube, it doesn't have B3 symmetry. Right now that feels stupidly obvious, but when we move to 4D, something weird is going to happen with that. Alright, time for 4D. We take the odd and even vertices of a tesseract to make the 2 4 demicubes. This compound has B4 symmetry, just like the other compound had B3 symmetry. If these demicubes were alone, they'd have B4 symmetry because they're 4 orthoplaces, but because there's another demicube dangling off of it, the demicubes only have D4 symmetry inside the compound. Let's put a 4 orthoplex dual to that starting tesseract. Now we have 3 16 cells in this compound because the 4 orthoplex is a 4 demicube. It just so happens that with this arrangement, all 3 16 cells are identical, meaning I can rotate it in such a way that any of the 3 16 cells are the outer dual one. Remember how the first 2 16 cells had D4 symmetry within the compound because of the other 16 cell dangling off of it? Now that there's another 16 cell, it's in the perfect spot such that all 3 16 cells have full B4 symmetry within the compound. It's pretty obvious that the outer dual one has B4 symmetry, so if you just trust that all 3 16 cells are equivalent, all 3 have B4 symmetry. I know the 2 demicubic 16 cells look smaller than the orthoplex one, but they're actually not. When a vertex appears close to the center but is colored strongly, that means it's further away in 4D, so it balances out. What about the compound? What symmetry does it have? You might think it has B4 symmetry, but you'd be wrong because there's an extra 3 cycle symmetry of mapping the 3 16 cells onto each other. I can rotate it such that the 3 cycle is visible, which I think helps it make more sense. Because this is B4 with an extra 3 cycle, we've tripled the symmetry group of B4. This is F4, the symmetry group of the 24 cell.
How cool is that?
This compound is called the stellated icosatetrachoron, and it has the vertices of a 24 cell. In case it wasn't obvious, you can't arbitrarily multiply symmetry groups by numbers. Simplices can double their symmetry group because they don't have opposite vertices, but the 2 cube and 4 cube are the only n cubes to have a symmetry group that can multiply, and by 3 is very strange. B2 can multiply by any arbitrary integer because all polygonal symmetry groups can do that by compounding a bunch of polygons at different angles. This means that, according to this definition of group multiplication, B4 times 3 is F4. It's worth noting that B4 is not a normal subgroup in F4, which means that transforming B4-wise changes the other two B4s. However, D4 is a normal subgroup in F4, so D4 times 6 is inarguably F4. Again, if you understand Coxeter-Dinkin diagrams, this has an extra layer of context. You might have wondered why F4 isn't B4 times 6, since a triangle has order 6 symmetry, not order 3. The reason is that the reflections are already part of the 16-cell symmetry, but not part of D4. F4 has an order 3 times larger than B4, for obvious reasons. I hope all that made sense. It is a phenomenon with no 3D version. I encourage you to pause or rewind and think about this until you really understand. Speaking of a 3D version, let's talk about analogs. The two most popular 24-cell analogs are the joined n-cube and its dual, the rectified n-orthoplex. Rectification is when you cut the corners of a polytope back until the new facets touch. It rectifies the facets and adds the vertex figure where the vertices were. So when you rectify a 16 cell, the tetrahedra rectify to 16 octahedra, and 8 octahedra are added. The cube and the octahedron are analogs of the 24 cell too, because their Schläfli symbols can have a 3 added to get the 24 cell. This is why I like to think of F3 as B3 rather than non-existent. This doesn't extend to B5 or Bn, by the way. It extends to the 24 cell tiling and then hyperbolic stuff. Anyway, yeah, that's the 24 cell. I'm a huge fan of it for having two sets of cubic axes rather than simplex axes and then something else. If you know of someone who has explained these things about the triple tesseractic symmetry in an intuitive and accessible way, please let me know in the comments so that I can show them support. As far as I know, I'm the first, which is both cool and kinda sad. Join me in part 3, Jesus Christ, part 3? This has really gotten away from me, where I discuss every dimension higher than 4. Thanks for watching. Oh, and by the way, you shouldn't join my Discord server, even if you want to. It has a ton of people already, and there's very frequent conversation. But I totally get why you would want to join. There's tons of cool people, and they post really cool stuff.